All right. Oh, I knocked it. So today we want to look at arc length and surface area, finding the arc length and surface area for arc length for a curve, the length along that curve, and then the surface area for curves revolved around the axis. We've already found the volumes of curves revolved around some axis. Now we want to look at finding the outside edges of those. Now, in order to do that, we're going to create a new dimension, right? So far, we're familiar with a couple. dx. dx is a little arrow that goes left to right, right? Tells you which dimension you're going horizontally, left to right. dy is a little arrow going bottom to top. And again, they're infinitesimal in size, right? They don't have any length. They're less than any given length. They're just like this little arrow, pure direction only, right? They're just telling you which dimension you're in and consequently what variable you're doing your operation with respect to. dr is out, right? Inside to outside, dr. Okay, so those are some that we've seen before. Those are familiar, particularly dx and dy, most definitely dx. But we've already seen that if I take some function, f of x, and integrate from left to right dx, I'm not going to get the length of that curve. I'm going to get the area underneath, right? So we've got to do something a little bit different. I can't just walk left to right dx. What I want to do is walk right along that curve. And as I go along the curve, add up the distance that I'm traveling as I go. Okay, so we need a new dimension. Instead of just dx or dy, I want a little arrow, ds, that's going to walk right along with the curve. As I walk left to right dx or bottom to top dy, I want the actual dimension that I'm working in to walk right along with that curve, ds. That's this little arrow. All those little arrows, they're walking right along with the curve. Okay, and ds usually I read that as with respect to the surface. So in this case, it's one-dimensional, it's a curve, right? Okay, so we need to figure out what this new dimension is. How do we get the arrow to walk along our curve? And not only do we need to figure out what that new dimension is, we want to be able to link it back to our familiar dx, because we know how to do stuff relatively easy, left to right dx. So if I want to do this stuff in the new dimension, I want to have a link back to my dx that's familiar. So it goes like this. Let me blow it way up. Let's say we've got some function like whatever. Okay, some function f of x. Let's look at it. It doesn't really matter where. I'm blowing this way up. Okay? So I'm looking at between these points, but we want to imagine that those points they're touching. They're the same point, essentially, right? So that this, left to right, this is dx. That horizontal arrow. That's dy, the vertical arrow. So it's a super, super teeny tiny little triangle here. The length that's walking right along with the curve, that's ds. Okay, so simple Pythagorean theorem tells us that ds squared is dx squared plus dy squared. A squared plus b squared is c squared, yeah? Okay, so this is getting me close. I remember my first the task that I needed to do was to define what this ds is. What is this arrow that's walking along with the curve? So I'm getting to it here. I'm actually able to solve it. ds is, strictly speaking, plus or minus, but we're talking about the length of the side of a triangle, so I have a reason to throw away the minus one. It's the square root of dx squared plus dy squared. Great. So here I've actually been able to say, what is this ds? This is good. It's the side of this triangle, and as these dy, like over here, here's my dx, here's my dy, here's my ds. So you can see that it's going to walk along with the curve. Great. But now I need a link. How does this ds operate if I'm just doing my normal left to right business, dx? So I need a link. This is a completely new dimension that I'm just inventing so that we can walk along that curve and add up the distance that we move. So we're here. ds is the square root of dx squared plus dy squared. Straight Pythagorean theorem. And now I'm going to multiply by 1. Now what I want is a link to dx. So I want to be able to get dx outside. I need to relate ds and dx. So I'm going to multiply by 1 here, square root, and I'm going to multiply by dx squared over dx squared. Oops, dx squared plus dy squared. Okay? So I have the square root of dx squared upstairs. The square root of dx squared is just dx, so I can pull that dx out. That was my goal here. This other one I'm going to distribute through. The 1 over dx squared I'm going to distribute through. So I have ds is, well, the square root of dx squared, I can pull that outside. It's the dx, square root. And I have dx squared over dx squared, distributing that through. And I have plus dy squared over dx squared. I'm very, very close. This is basically done, but I can simplify a little bit. I've got ds is the square root of 1 plus, well, dy dx, that's the derivative of the function. That's with respect to x, right? It's df, or f prime, to simplify it here, f prime of x, the derivative of our function with respect to x, dy dx, squared dx. So here we have defined ds. Well, there was our definition of ds. And now we have the link between ds and dx. So we can do our familiar dx business, left to right, a to b, no problem. And as we're doing that, our ds is going to walk the curve. It's going to do that triangle business here. Okay. So one thing to note with this with ds is we need the derivative in order for ds to work, right? It's part of that formula. So if we're looking at a function on a certain interval, we have to be careful that that derivative is actually defined. We need it in order to define ds. So if that function isn't, or if the derivative isn't defined on the interval, we can usually just go dy instead, just change your direction. And instead of taking the derivative of y with respect to x, we just take the derivative of x with respect to y, dy, right? Just reverse. Okay, we'll see an example of that later. So the arc length for some function from a to b of f of x, so of some function f of x on an interval from a to b, right? Well, we're going to take these little arrows that walk along the curve, those lengths, and just add them all up as we go. So it's the integral from a to b ds. Walk along that curve and just add up all the distances that you get. Well, practically speaking, we're generally given some function of x or some function of y, not of this s that we invented for our own purposes. So that's why we need this link here. Sure, the arc length is just integrate as you walk along the curve, ds, but what does that actually mean in terms of dx? Well, it's the integral from a to b of the square root of 1 plus the derivative of f squared dx, right? This is ds. Now, there's our formula. The setup is generally not too bad because we just need to find our derivative. We need to be careful that it's defined on the interval a to b. But otherwise, the issue with these is that we're always stuck with this composite, right? We always have a square root of some function underneath or something underneath. So usually that's a difficulty. For where we are right now, we don't have the skills yet to deal with any random root of the sum of two squares. Later on, we'll get that skill, but right now we have to very much cherry pick what problems we're able to do, otherwise we'll just get completely stuck. And they end up being algebra heavy. That's the difficulty with these problems. It's not so much the setup, it's we've got to jump through algebra hoops and try to do everything possible in order to get out from under that root, either to get a perfect square and eliminate it, or to u sub for whatever's underneath. If I can u sub what's underneath here, then I'll just have u to the 1/2, and it's this power rule, 2/3 u to the 3/2, and we're done. But in order for that u sub to work, the derivative has to be outside, or it just has to be a linear function, in which case the derivative is a constant and it doesn't bother me. I can just pull the constant outside. But that's usually the difficulty with these, is that we're jumping through algebra hoops, doing everything we can to either u sub what's under that root or get a perfect square or get out from under it somehow, okay? That's the actual difficulty with these. So let's try, let's find the arc length of y equal ln cosine of x on the interval from 0 to pi over 4. All right. So in order to find the arc length, it's just going to be the integral ds, but in order to do that, I need the derivative of f. I need the derivative of y here, okay? So I need dy dx. This is a chain rule. So the derivative of ln of u is 1 over u, so 1 over cosine of x. And the derivative of the cosine is negative sine. There's my chain rule. So the derivative of the outside times the derivative of the inside. A sine over cosine is tangent. All right, so I know what the derivative is. Now I should be able to set up. We have the integral from a to b, integral from 0 to pi over 4, square root 1 plus my derivative squared dx, and the derivative was negative tan x. Now the tangent is defined on the interval from 0 to pi over 4. It's at the pi over 2 multiples where it goes undefined. So we're okay there. And now that is the integral from 0 to pi over 4 square root of 1 plus tan squared of x dx. Now, this is where we're in a little bit of trouble. I can't u sub for tan squared plus 1. Well, what's the derivative of tan squared? Secant square? Or the derivative of tangent secant? Yeah, we'd have to do a chain rule with that. Anyway, I don't have it outside is the point. There's nothing else outside here, so the u sub's not going to work. So this is starting to ring a bell. 1 plus the tangent square. I'm starting to think that's familiar. That's ringing something from trig. Let's see if I can substitute for that. There's really only one rule that you need to remember, and you can get the other two. It's the cosine square plus the sine square is equal to 1. It's a Pythagorean identity from trig. Cosine squared plus sine squared equals 1. If you remember that one, then we can get the other ones just by dividing. If I divide by cosine square, this will be a 1. Sine over cosine is the tangent square, and then 1 over the cosine is the secant squared. Ah, well, there I'm recognizing that structure. And then just to be, for the sake of completeness, if I divide it by the sine, I get cosine over the sine, which is the cotangent, plus sine over sine is 1, is 1 over the sine is the cosecant squared. So that's the other one. But this is the one that we were hoping for right there. That 1 plus tan squared x is just the secant squared. So integral from 0 to pi over 4 square root of the secant squared dx. And now I'm happy because I have this square root of something square. Get rid of that root, and I just have the integral from 0 to pi over 4 the secant of x dx. And that's one of our basic rules. Well, not so basic, but it's one of the fundamental rules. Integrating secant is ln absolute value of the secant of x plus the tangent of x, and this is barred at pi over 4 and 0. All right, now, yeah, everything has an x in it, but these are trig functions, so the second ones don't necessarily all just zero out. We'll have to actually evaluate and see what happens. So let's see, we have ln secant pi over 4 plus tangent pi over 4 minus ln absolute value. Now I'm evaluating at 0. Secant 0 plus the tangent 0. Okay, so there's my antiderivative evaluated at b minus antiderivative evaluated at a. Ln absolute value, let's see, secant is 1 over the cosine. Cosine of pi over 4 is root 2 over 2, so reciprocal. Simplify, this is root 2, yeah? Tangent of pi over 4 is the sine of pi over 4 over the cosine. So they're the same there, root 2 over 2. So a tangent there is just 1. Minus ln, let's see, the secant of 0. Secant is 1 over the cosine. Cosine of 0 is 1. So 1 over 1 is 1. Secant of 0. And then the tangent of 0, well, it's the sine over the cosine. Sine of 0 is 0. Cosine of 0 is 1. So 0 divided by 1 is 0. Tangent of 0 is 0. Well, this is ln of 1. ln of 1 is just 0, right? ln of 1 is 0. So that did end up zeroing out. ln of, well, square root 2 plus 1 is a positive number, so its absolute value is just what it is. And so that's it. ln 1 plus root 2. And we could get a decimal approximation to whatever that is. And now that's the arc length, so that's units. Just units. It's a length. Okay, again, the setup was relatively easy. We just had to find the derivative and plug it into our formula. The hard work is the algebra or the hoops that we need to jump through in order to get out from underneath that square root. Let's try. Let's try. How about y is equal to x to the 5th over 10 plus 1 over 6x cubed. Yeah, again, I can't just make these up. I have to steal them. Otherwise, the likelihood is that we'll get stuck. So like, we really got to cherry pick our examples. 2 to the 5. Okay. So I'm trying to integrate from a to b root 1 plus the derivative squared dx. That means I'm going to need this derivative, so we might as well just do that, yeah? So the derivative of y, see the 5 over 10 will be over 2, subtract 1, x to the 4th. Now this is an x to the negative 3, so we'll get a negative 3, looks like a minus a half, like 3 over 6, and then subtract 1 is a negative 4, so x to the 4th downstairs. Yeah, so there's our derivative. Now we can set up our arc length. So the integral from 2 to 5, square root of 1 plus, here we need our derivative squared dx. We'll put our derivative in there, x to the 4th over 2 minus 1 over 2x to the 4th. All right, this is our arc length. There's our setup. That's not too bad. The setup isn't too bad. The trouble is that we've now got all this mess underneath the root there. So that's what we're on about now. We're just basically doing algebra, trying to get out from under that root. So let's see what we got. Integral 2 to 5 root. We've got 1 plus. So square that, x to the 8th over 4. X to the 8th over 4. Now multiply them together. So we'll get minus 1 over 4, but then multiply by 2. So 2ab right in the middle. So the x over 4 over x over 4, those will become 1. We've got minus 1 over 4, but multiply by 2. So minus a half. And then square 1 over 4x to the 8 dx. We do have some like terms there. 2 to 5 square root x to the 8 over 4 plus a half, right? 1 minus a half plus 1 over, did I? Yep, 4 x to the 8th dx. Okay. So we distributed out and combined our like terms, simplifying that function as much as we possibly could. Now we're very much in deep doo-doo. Well, we need a trick. Because I have all this mess still underneath that root, yeah? So there's a strategy, the most common strategy that we're going to use here is factor out the least power of x. So we have an x to the negative 8th power there. If I factor that out, I can pull it outside and we'll see what happens. Okay, so that's what I'm doing. I'm pulling out the least factor of x. So 2 to 5 square root. Now I'm going to pull out x to the negative 8. That's the least power of x here. X to the negative 8. Well, that'll give me x to the 16th. X to the 16th. Oops. Because 16 minus 8 will give me that 8. Over 4. This chalk is acting weird. Over 4. Plus, well, I need the 8s to be to the 0, right? There's no x in here. So 1/2 x to the 8. 8 minus 8 will 0 and give me a 1 there. And then I already had an x to the negative 8 in this one, so this is just plus a quarter dx. And now this is a perfect square. So I can take the square root, just divide by 2, and pull that outside here. Not outside of the whole thing, but outside of the root. So I've got 2 to 5, x to the negative 4. Let's take the square root of negative 8. And underneath, I've got this function here. Now, this is quadratic-like. Look, 16th, 8th, and 0. So this looks like it's a perfect square. We could pull out of 1/4 and take its square root, and then it becomes even more obvious. It's x to the 16th plus a half x to the 8th plus 1, right? But let's say we didn't. Let's just see this is quadratic-like. This is x to the 8th over 2. Oops, x to the 8th over 2. If I square that, I'll get that. If I square that, a half, I'll get a quarter. And now let's just double check that our middle term works. So if I multiply these two guys together, I'm going to get an x to the 8th over 4. But then I have to multiply by 2. So x to the 8th over 2, that works. It's a perfect square. So square root of the square goes. And now I am in a much better position. 2 to 5, x to the negative 4 times x to the 8 over 2 plus a half dx. Okay, so I'm getting close now. I'm just going to distribute that through and we'll end up doing power rules. All of this algebra, that's what I was saying, the setup isn't all that bad. It's jumping through the algebra hoops in order to get out from under that square root. That's the difficult business. Okay, but we're getting close now. We've gotten rid of this square root. So we're here, 2 to 5. 8 minus 4 would give me x to the 4th over 2. And I might as well just leave it x to the negative 4. So that way we can do a power roll. Dx. So let's see, x to the 5th over 5, so that would be a 10. Okay, we got to add 1, that's going to be a negative 3. Divide by the new power, so this is going to be a minus 1 over 6. Minus is over 6. So add 1 gives me a negative 3rd power. Divide by the new power, flips the sign, gives me a 6. Okay, good. Barred at 5 and 2. Really, I should probably just drop that down in order to make our evaluation easier. But now we're actually just evaluating it. So 5 to the 5th over 10 minus, well, it's going to be 1 over 6 times 5 cubed minus 2 to the 5th over 10 minus, it's going to be 1 over 6 times 2 cubed. Okay. I'm tempted to just give up right there because we're just evaluating at this point, but for the sake of completeness, we'll just finish it out here. 5 to the 5th. Ooh, I think, nope. Ooh, my battery is toast. My calculator batteries are toast. Okay, well, I'm just going to leave it there then. It won't, yeah. I should have checked it. Okay. Anyways, we're just evaluating calculator from there. Anyway, we've done the hard work, the setup, and then the algebra to get out from under that. The strategy there, pull out the least power of x. That's usually the most frequent strategy we can use. Let's look at one more here very quickly. How about y is x to the 2/3 plus 1 on the interval from 0 to 8. Well, we know in order to find this arc length, we're going to need the derivative. So y prime, let's see, 2/3 x, subtract 1, so negative 1/3. Derivative constant is 0. But this is a cube, it's a cube root of x in the denominator. It's downstairs. So we're kind of in trouble. Well, we were very much in trouble because the derivative, we need the derivative in order to define the arc length, but the derivative is undefined at 0. I can't, right? The derivative is not defined at 0. So instead, I'm going to go dy. I'm going to say, well, my derivative dx is undefined on that interval. So let's flip intervals. Let's look at it dy and see if that'll work. Okay, so I did my derivative, checked that it was defined everywhere on that interval, and it wasn't. It's not defined at 0. So I'm going to switch. I'm going to say, well, okay, if x is 0, y is 1. If x is 8, I'll take the cube root of 8. That's 2. 2 squared is 4. 4 plus 1 is 5. Okay, so that's on the interval from 0 to 8, the y goes from 1 to 5. And I need to solve this then for x as a function of y. So y minus 1 is x to the 2/3. And if I take the 3/2 power, x is y minus 1 to the 3/2 power. Okay, so we've solved for x as a function of y, and we found our y bounds. Now, before we had our function of our y as a function of x and our x bounds, and then we needed to take the derivative of y with respect to x. Well, this time we've switched it. We now have x as a function of y bounds. So we need to take the derivative of x with respect to y. What we have here, so we're just looking at x prime, right? We're looking at the derivative of x with respect to y. It's a composite function, so chain rule. But the inside derivative, right, the derivative of y with respect to y is just 1. So it's really just the outside. 3/2 y minus 1, subtract 1, so the 1/2 power. Now, it's multiplied by 1, right, because the derivative of the inside is 1. But, okay. So we took the derivative of x with respect to y. Great. Now we can actually set up our integral. We have integral our y bounds 1 to 5 with the square root of 1 plus our dx dy, our derivative of x with respect to y. So 3/2 y minus 1 to the 1/2 power squared dx. And now I'm looking at that one and I'm going, that was a really nice choice. Even though I had to do the algebra work over here, now that square root underneath there, that's just going to go. So I think things are going to be very simple, right? The square root squared, that's just y minus 1. So hopefully we'll be able to just do a nice u sub here. Let's see, 1 plus, we've got 9/4, square that up. And then square that up, y minus 1. Oops, sorry, this is dy this time. These are y bounds. I got a function of y, so this is dy, my fault. So, integral 1 to 5, root, we have 9/4 y, and 1 minus 9/4, 4/4, minus 9/4, negative 5/4. Force a habit. dy. Well, this is just a straight up linear function. I can do a u sub, no problem here, right? Because my derivative is just a constant, and I can always pull the constant out. So let me show you what I mean. 1 to 5 integral. We have this 9/4 y minus 5/4 dy. So we're here. And I'm saying, well, just make u whatever this is. It's u. 9/4 y minus 5/4. So du, derivative of constant is just 0. It's just 9/4 dy. This constant never bothers me, right? It's just 4/9 and I can pull it outside when I sub for this dy. So 4/9 du is dy, this dy here. And I can pull that outside. Okay, so that's what I'm going to do. I'm going to do this straight u sub. And I'll say integral. The 4/9 is going to get pulled outside. That's from my du sub. And I just have u to the 1/2 power. So this will be a straight power rule. Since I'm doing a u sub though, I need to change my bounds yet again. First we had to change them to y bounds, but now I'm u subbing, so I got to change them to u's. let's see, if y is 1, then we have 9/4 minus 5/4 is 4/4. U is still 1. And if y is 5, we have 45/4 minus 5/4 is 40/4. 40 divided by 4 gives me 10. And now we're at power rules. 4/9 times, what is this? U to the 3/2, add 1, and then divide 2/3, barred at 10 and 1. Okay, and then from there, we're just evaluating, right? That's the setup. We did the hard work. We got to the U sub. Now we're just plug and chug evaluation stuff. Okay. So again, that can happen. That was what I was saying in the beginning, is that we need that derivative in order to define the ds. So that derivative has to be defined on the interval that we're looking at. If it's not, we'll just switch and look at the same function, dy. And that'll work usually. Nice. Okay, so I'm going to split this apart, and in the next video we'll look at some examples of our no, this was arc length, sorry, of the surface area part.